In this question number 2, we are given these neutralization reactions. So we are asked to define enthalpy change of neutralization. The first thing you will realize is there is no mention of standard there. So that means you don't get marks for mentioning standard conditions. In fact, you may even get penalized for mentioning standard conditions when the question did not have that data, did not even ask you about standard there. So you got to read the question very, very carefully. So we know that neutralization is to do with the amount of water formed when the acid and base reacts together. Sorry, I mean the acid and the base react together, not the other way around. But here you're producing 2 moles of water, and that is the key focus here. When you get the unit in kilojoule per mole, the per mole is actually for 1 mole of water. So a lot of the thing in enthalpy change definition is to do with 1 mole of something. Here is to do with 1 mole of water, so you must really specify that very, very clearly. So here we have the enthalpy change. Enthalpy change for forming 1 mole of water. And how do you get the 1 mole of water? You will get the 1 mole of water when acid and bases react. When acid and bases react. And I want to say standard conditions, but I don't get the standard in the definition. So I do get 1 mole of water. I do get the idea about acid and base react. So even though one of them is limiting, you need to get the correct multiple of water, the correct mole of water. Then you get the enthalpy change with the energy release or energy change, dividing that by the mole of water, so that you get kilojoule per mole of water. That's very, very important there. I believe that if you write understand the conditions, you don't get penalized, you don't get rewarded, because there is no mention of standard in the question at all there. Okay. In part B, we are supposed to do some calculations. These are typical practical question in paper 3. So inside our cup, we have solution plus solution. So be very careful about this idea here. A lot of students, they think that it's just one solution, but there are 2 solutions. So first of all, you have this already in the cup. You have the sulfuric acid already in the cup. This is 75 cm cube of 1.00 mole per dm cube H2SO4. So what are you going to add into it? You are going to add in 100 cm cube of your NaOH, so it's 1.00 mole per dm cube NaOH. So we have our initial temperature Ti. This is our, hang on, what is this? Our thermometer would have been in the cup. So the initial temperature would have been the initial temperature of the sulfuric acid, and this thing really wouldn't matter what the initial temperature of the NaOH, because this is to add, whereas this is already in the cup. So therefore we depend on where your thermometer is for our initial temperature. But as you can see, they are both at the equal temperature, so it doesn't matter which one you use. So this is the maximum temperature. It has risen. It has risen because neutralization is exothermic, which means that it releases heat energy to the surrounding, and therefore the temperature of the surrounding will increase. It will get hotter there. So now use equation 1 to calculate the amount in mole of sulfuric acid that is neutralized in the experiment. If we look at the mole ratio, we can see that 2 mole of NaOH reacted with 1 mole of sulfuric acid. So given that we started from the same concentration, and then we should expect that the volume of NaOH would be double the volume of H2SO4. So 75 cm cube of sulfuric acid should require 150 cm cube of NaOH. So we can think about 75 cm cube of H2SO4. It would need 75 times 2, which is 150 cm cube NaOH, simply and only simply because they have the exact same concentration here, and the mole ratio is 1:2. So looking at this question, we only have put in 100 cm cube of NaOH. So that means not enough NaOH, and therefore NaOH is limiting. Sulfuric acid is in excess. So sulfuric acid is in excess. By how much is it in excess? Well, if you only have 100 cm cube NaOH, 100 cm cube NaOH would only need 100 dividing that by 2, which is 50 cm cube H2SO4. So only 100 divided by 2, which is 50 cm cube H2SO4 reacted instead of the whole 75 cm cube. So having done that mole ratio and working out the limiting reactant, and therefore we know H2SO4 is in excess, the question now is how much is it reacted? Well, the mole of sulfuric acid reacted is going to just be 50 cm cube. So that is your CV, the concentration of the sulfuric acid, 1.00 mole per dm cube. Multiply that by 50 over 1,000, and just pressing that into the calculator, get 0.05. By right, if you look at the number of significant figures, 1, 2, and 3, 1, 2, and 3, I should really give my answer to 3 significant figure just to be consistent and also appropriate number of significant figure as stated in practical chemistry and also in the calculation topic of the syllabus. Now calculate delta H neutralization using the results in table 2.1. The reason I think they asked us to work out the amount of sulfuric acid neutralized, even though sulfuric acid was in total excess, but we now know how much of it get neutralized, and that is not really giving us 1:1 mole ratio, is it? Oh well, we know the NaOH is limiting because we know sulfuric acid is in excess. So if that is true, so that means when we react however much sulfuric acid, the mole of water is 2 times the mole of sulfuric acid. 1 mole of sulfuric acid reacted, that is 2 times the mole of water. So I need to work out the mole of water first. So the mole of sulfuric acid is to the mole of water. It was 1 mole sulfuric acid giving me 2 mole of water. How much sulfuric acid actually get neutralized? 0.05, and this is X. So therefore X is the mole of water that get produced. That is going to give me your cross multiply. 1 times X is X, 2 times 0.05. That gave me 0.1 mole of H2O. And the second part would be your calculating the Q equal to MC delta T, where this is of the water of the solution. So we need to be very careful about this experiment. We are adding 100 cm cube to 75 cm cube. So altogether, there is total volume of solution. So even though the sulfuric acid is in excess, but there is got this much solution inside, this much water inside. So however much energy that get released would have gone to all the water. Even though the sulfuric acid is in excess, it still contains water that is going to be heated up in the solution. We also know the density of water is 1 gram per cm cube. So that means that there is going to be 175 gram of water of solution. So there is your M there, which is 175 gram. Multiply that by 4.18, and then we multiply that by the change in temperature. We look at Ti and Tf. If you follow this final temperature minus initial temperature, you get 7.8 degrees Celsius. We also know that the change in temperature is relative because it's something minus something. So that means the change in temperature in degrees Celsius is the same as the change in temperature in Kelvin. If you don't believe me, you can set up a lower secondary mathematics kind of number line, and then you have like 0 and 25 degrees Celsius. The difference is 25 degrees Celsius. And then you have 273 and 298 Kelvin. The difference is still 25 Kelvin. So the change in temperature is a relative scale difference there. So it doesn't matter the thing there. We do not need to add 273. So our difference there was 7.8 degrees Celsius. Plugging that into your calculator, so 175 times 4.18 times 7.8, and I get 5705.7 joule. So a bit of confusion there. I mean, we know the sulfuric acid is in excess, not all the sulfuric acid reacted, but you got the sulfuric acid remaining that has got water component. So that's why we have to total up the volume of solution here, because it's solution plus solution, giving us the total mass of water that we are heating up. So after you do all that, I think we are ready to work out the enthalpy change of neutralization, which is in kilojoule per mole. So 5705.7, dividing that by 1,000, That will give you your kilojoule. Don't forget to divide that by the mole, which is 0.1 mole of water. And do not forget to put in the sign, because you gotta have sign, value, and also unit. So the sign there is going to be negative, as this is an exothermic reaction for neutralization, exothermic reaction as the temperature rises. So 5705.7, dividing that by 1000, dividing that by 0.1, and I get the final answer to be minus 57.057. I should give my final answer to 3 significant figures, consistent with all the data given in the question: 4.183 sig fig, 1.00, 1.00 there. Those are the density of water as mentioned earlier in the question. So this will give you minus 57.1, and this will be in kilojoule per mole, which I've just stated above there. And my answer will have a sign, a value, and also a unit. If you've done enough enthalpy change or neutralization, you will know that give or take strong acid and strong base is around minus 57 kilojoule per mole. So a bit of general knowledge there, which you're supposed to know if you've done enough AS content revisions on enthalpy change and neutralization between strong base and strong acid. It's usually around minus 57 kilojoule per mole there. In C part 1, complete the equation for what occurs when you have barium hydroxide. So this is again another very strong base around pH 14, and this is part of group 2, solubility of hydroxide. So this is also strong acid and strong base. So we will expect the similar kind of enthalpy change or neutralization. You will get barium sulfate, which is a solid. Because of solubility rules of sulfate, it decreases down group 2, and you still have producing liquid water, of which the barium sulfate is insoluble in. Gotta balance the equation: Ba2 plus, Ba2 plus, SO42 minus, SO42 minus, 1:1 mole ratio. 2 of the H plus, 2 of the OH minus, therefore I'm gonna get 2 of the H2O. Now there is 1 and 1 of that, and the stat symbols are as included, including the stat symbols based on the question that they're asking there. Now last part, suggest why the enthalpy change and neutralization cannot be determined by using the addition of dilute sulfuric acid to aqueous barium hydroxide, simply because barium sulfate is an insoluble white solid, it's an insoluble solid. And if that is an insoluble solid, therefore we don't know, or we cannot know for certain if the heat energy release by the neutralization, as neutralization is H plus plus OH minus, without breaking any covalent bond, but forming the OH covalent bond in water. Ionic equation, H plus plus OH minus giving you water, just forming covalent bond without breaking anything is going to be exothermic overall. So there's heat energy released by neutralization, would just be totally heating up the solution. Okay, would just be totally heating up the solution rather than the solid as well. So we are saying that we are producing something else which is no longer in solution, and therefore we don't know if all the heat energy release could be used for just heating up the water, which is what we did Q equal to MC delta T earlier, our calculation for just the solution. When the salt was soluble in the solution, there was no precipitate. But barium sulfate, O level, IGCSE level, paper 3 practical, paper 4 alternative to practicals. So at those level, you have learned that sulfate there, test for sulfate, giving you the white precipitate. In AS practical, you also learn the test for sulfate, SO42 minus, adding acidified barium nitrate or acidified barium chloride, white precipitate there. Okay, that's it ready for that 9 marks overall question.